Okay guys, so in this next video is 7.2, it's rotations and volume. It is one of the last, actually it is the last section that we'll be covering for preparing for the AP exam. We will be, after this we'll be reviewing for our exams. And I will have those available for you, the reviews here pretty quickly. I'm going to try to have them up sometime midway in the first week of April. So today, like I said, is rotations and volumes. So I'm going to go ahead and first I'm going to start off with what the heck is we're doing. So what we're essentially doing is we're taking some excuse me, some curve. So that's my curve. And then we're going to rotate it around an axis. So if sometimes we'll rotate it on the x-axis or rotate on the y-axis. In this case, we're going to rotate it on the x-axis. And that's going to spin this shape around, creating this three-dimensional shape that looks something like this. So, I don't know, that kind of looks like a lampshade to me. But this is a shape that we're going to be creating. We're going to find the volume of this shape. Now, the way we do this is we're going to find the integral of pi, we'll say r square dx in terms of x, from some value a to some value b. A would be the starting point, B would be the end point. Now, if you look at this, you'll notice that it looks very, very similar to a circle. Well, it is because it's exactly what it is. It is so if we take a slice of this shape right here, we would get, and put it flat, it would be a circle, which is why our formula looks an awful like a circle. That's why we say it's pi r squared. And this distance right here, we call this change right here, we call this dx, and that's going to be our defined radius by our function, which is defined by our function. So let's go ahead and start off with something a little more simple. We'll start off with the function equals square root of sine x. Now, one thing I'm going to remind y'all is in these videos, I'm just going to get to the setup portion because I know y'all can integrate just fine. I just want to set it up for you so I have more time to do examples. Okay, so what we're going to do now is to set this guy up. We want to, and often it'll tell you where you want to along what lines you want to rotate it. So in this case, we'll go from 0 to pi. So my integral then would be pi 0 to pi from 0 to pi, and then my function square. Well, my function in this case is square root of sine x square dx. And then I'll just simplify it really quickly. This square and this square cancel out, so we get pi integral from 0 to pi of sine x dx. I'm going to leave it at that because, like I said, I have confidence in y'all's abilities to go ahead and integrate. Now, the other thing we have to be aware of is that we're not always going to be rotating around the x-axis itself. A lot of times we'll be rotating around a certain line. So the example I could give you is, let's take the function, this is 2 minus x squared, and we're going to rotate it along the line g of x equals 1. Okay, so what I'm going to do here is we're going to rotate it. Since we're rotating on this line, we have to manipulate it a little bit. So what I'm going to do is we're going to, when I set this up, pi integral from, I'm going to go ahead and tell you the bounds, it's from -1 to 1. And what we're going to do here is our range is the area between two curves. Well, this region right here is 2 minus x squared minus 1 square dx. Because this is my distance between this point and this point is defined by the difference between this function and this function. So this minus this square will be my function. I can simplify that by saying pi integral from -1 to 1 of 1 minus x squared square. And this is what I will use to actually integrate my problem. And now, just as a hint for y'all to we're going to actually work this out, I would go ahead and split this up like this, and then distribute it normally, and then integrate. Okay, so the next example I want to set up, helps you set up, is what happens when we have two separate functions. Say square root of x and x squared. What are we going to do then? Well, the formula between two, so when I rotate this around, it's going to look something like this. Sorry, it's not the exact drawing, but there we go. So we essentially have this bowl with a funnel looking thing in the middle as our three-dimensional shape. So what we're going to do here is a general formula for what's called the washer method, because when we slice down the middle right here, we get a shape that looks like a washer. This distance right here we call our radius. This is r, this little r. This distance, this change is dx. So we're going to go from 0 to 1 of our outer radius. So in this case, the outer radius is the square root of x square minus our inner radius, which is, in this case, x square dx with pi out in front. And that's how that one's going to work. So the general form for that would be pi a to b of the outer function square minus the inner function, or inner radius. So a lot of times you'll see textbooks do this. Big R minus little r, symbolizing the outer radius and the inner radius. And that's going to be your general form for what's called washer method. Over here, what I taught you earlier, this is called the disk method. Okay, so now that problem is, we'll simplify it, and then y'all, like I said, have the ability to integrate at a high level of proficiency now. So I am not going to integrate that one. Y'all can handle it from there. Okay, so the last problem I do want to go over is one that rotates around the y-axis. So what do you do when you have to rotate around the y? So this is what we'll do here. Here's my shape. So we have x equals 1, and then we have the function x squared plus 1. All right, so what we're going to do here is I'm going to actually split it up into two different volumes. So I have this guy and this guy. And this is to the value 2. So when I rotate it around the y-axis, let's go from 0 to 1 first. The integral from 0 to 1 of 1 dy. Notice what I'm doing here. It is dy, not dx, because we're rotating around the y. And my values are from this 0 to this 1 right here. 0 to 1. And this value is defined by x. So that is the setup for this rotation right here that creates a a cylindrical base. And if you want to look at a better picture of that, you can do 458 in your textbook. It's there for you. All right. Now, if you look at the next one, let's look. So this is this guy right here. Now let's go ahead and do this guy. So it's going to be pi integral from 1 to 2, this y value 1 to this y value 2. And now I can't, so top minus bottom, sorry. The x function here is 1 square minus bottom. Now here's the thing though. This is in terms of x. We have y equals x squared plus 1. We can't have that because it's in terms of y, so I actually need to solve for x. So y minus 1 equals x squared, so square root of y minus 1 equals x. So right here, I'm going to do y minus 1 squared dy. Okay, so this is the top function here, the bottom function here. It's the outer radius, so this is the 1 right here is the outer. This function right here is the inner radius. So that's the way I have to work that one out. I'm going to simplify that one real quick. Pi integral from 1 to 2 of 1 minus y minus 1, because the square and square root cancel out. I'm going to leave it like that. Like I said, you'll have the ability to integrate pretty. I feel confident in your abilities. Okay, so what we're going to do is on the first few problems, all I want you to do is set them up. So on page 461, I want you to, on numbers 5 through 8, just set up the integral. That's it. Set up the integral. On problems number 9 through 12, you're actually going to evaluate 9 through 12. And then the last few problems, what I want y'all to do is just work out individually. So that's the 13 through 16. So it's the same equation being multiple times rotating around different axes, the x-axis, y-axis, and then around a secondary, another line. And if you have questions, I'll be on my office hours. And if you can't make those office hours, email me. We can set up something in the afternoon and go from there. And if you're using a phone, you can get into the Google Meets using a phone number. So please contact me, email me, and let me know. We can work something out, I promise.